Hello students, I am Dr. Harjinder Singh, Assistant Professor in Chemistry. This is a first lecture in your physical chemistry course, and the very first chapter of your physical chemistry course is quantum mechanics. Now in quantum mechanics, the very first chapter is or the very first topic is black body radiations. So in this video lecture, we will see what is quantum mechanics and what are these black body radiations. So let us start. Okay, first of all, now since we are dealing with the black body radiation, so it is very important to know that what are radiations. Now the word radiation, this word radiations are basically a name for electromagnetic radiations. Now what are electromagnetic radiations? As we all know, these are the radiations which are having both electric field and magnetic field, and both these electric field and magnetic field, they are perpendicular to each other. So these radiations which are both having magnetic field and electric field, they are called electromagnetic radiations. Now the earlier, these properties of electromagnetic radiations were explained by classical theory. So the classical theory was the very first theory which was used to explain properties of these electromagnetic radiations. And this classical theory says that electromagnetic radiations, they are continuous radiations. Now the continuous means they can be emitted or absorbed in a continuous manner. So it believes that radiations are continuous in nature. This classical theory, which believes in continuous nature of these electromagnetic radiations, it can explain the phenomena such as diffraction of these electromagnetic radiations and interference of these electromagnetic radiations. However, this classical theory does not explain black body radiations, photoelectric effect, variation of heat capacity of solids with temperature, atomic spectra. So these properties or these phenomena, they are not explained by classical theory. So I am repeating all these things. Electromagnetic radiations are those radiations which are having both electric field and magnetic field. The very first theory which explained the properties of electromagnetic radiations was classical theory, and this classical theory says these electromagnetic radiations, they are continuous in nature. That means they are emitted or absorbed in a continuous manner. And this classical theory, it can explain the phenomena like diffraction and interference of these electromagnetic radiations, but it is unable to explain black body radiations, photoelectric effect, variation of heat capacity of solids with temperature, and atomic spectra. So in view of limitations of this classical theory, the another theory was given by Planck, and this is called Planck's quantum theory of radiations. So what are the main postulates or the main assumptions of this Planck's quantum theory? The very first assumption is radiation energy is emitted or absorbed not continuously. So this is very important. These electromagnetic radiations, they are emitted or absorbed not continuously. Here they are continuous, but discontinuously in the form of small packets of energy, and these small packets of energies are called quanta. So what are the quantas? These are the small packets of energy in which the electromagnetic radiations are absorbed or emitted. Now from this word quanta, quantum is arises. The second assumption of this Planck's quantum theory of radiations is the amount of energy. So we have already said the energy is not absorbed or emitted continuously, but it is emitted in form of small packets of energy called quanta. And the amount of energy associated with these quantas is directly proportional to the frequency of electromagnetic radiations. So if nu is frequency, so according to this point, the energy is directly proportional to frequency or if we remove this proportionality sign, we can write E is equals to h nu, where h is a constant and it is called, we all know, we are called, it is Planck's constant. So here h is a constant and called Planck's constant. So according to the second assumptions, the energy is directly proportional to frequency of light. So more frequency of light, more energy. Or you can say E is equals to h nu, where h is a Planck's constant. The third assumption of Planck's quantum theory of radiation is a body can absorb or emit energy only in terms of integral multiples of quantas. That means this h nu, this amount of energy is called one quanta, and the amount of energy which is absorbed or emitted, it's an integral multiples of these quantas. That means it is not fractional but it is integral. So here we can write, according to this assumption, E is equals to n h nu, where n is any integral number starting from 1, 2, 3 and so on. So it's an integral number, not it's a fractional number. So it's not a fractional. Fractional means like 1.1, 2.2. No, it is an integral number. So energy is absorbed in this integral form. So energy can be either h nu, or it can be 1 h nu, 3 h nu, 4 h nu and so on. So these three are the basic assumptions of Planck's quantum theory of radiations. Okay, so now next move to the black body radiation. So let us see what are these black body radiations and how classical theory failed to explain black body radiations. So it is our general observation, when we heat any solid or matter, it emits radiations over a wide range of wavelengths. For example, if you heat iron rod, if you have an iron rod, so it's a very common observation. So if you have an iron rod and if you heat this iron rod at some temperature, so what will happen at some point when you start heating? Firstly, it become red. After that, it become yellow, and at a very high temperature, it becomes blue. So if you heat iron rod, first it gives you red color, then yellow and blue. That means it is emitting a wavelength of light, or it is emitting light of certain wavelength. Okay, now the ideal body is which emit and absorb all frequencies. That means if you heat this ideal body, it will emit all possible wavelengths or all possible frequencies, and it also absorb all possible frequencies. So the ideal body which emit and absorb all frequencies or wavelength is called black body. So that's why it is called black body. Now black means it will absorb all frequencies or all wavelength. So when you heat it, it will emit all those frequencies or wavelengths. For example, here iron rod is not a ideal black body because it can emit only certain wavelengths like red, yellow and blue. But the perfect body, ideal body, which can emit and absorb all frequencies will be called black body. So how this perfect black body will look like? Now the perfect black body is a hollow sphere which is blackened from inside and having a very small hole in spherical wall. So the perfect black body will look like this. So this is a perfect black body. So it is spherical in shape with a very small hollow opening, and from inside it is completely black. So that when the light enters, or the electromagnetic radiations of any wavelength enters inside this perfect black body, what will happen? All these wavelengths or all these radiations, these are absorbed by this black body and none of it is escaped. So all radiations are absorbed, and when we heat this black body, all these absorbed radiations will be emitted. So such kind of body is called black body, which can emit and absorb all frequencies of radiations. And the radiations which are emitted by black body upon heating at particular temperature are called black body radiation. So it's very clear what are black body radiations. These are the radiations which are emitted by black body when it heated to a particular temperature. So it absorbs all kind of radiations, but when heated it emit all kind of radiations, and those emitted radiations are called black body radiations. Now, the important feature of these black body radiations are they're independent from the nature of material. That means material may be any, and they depend only upon temperature. That means these radiations which are emitted, they are independent from the nature of the material used in the black body, but they will depend only upon the heating temperature. So let us see what are the distribution of energy in black body radiations. Now the distribution of energy in black body radiations are given by this graph. Now this graph shows the distribution of the energy in black body radiation. Upon horizontal axis there is a wavelength, and upon vertical axis this is a energy density per unit area of black body. So you can see in this graph the energy density of or the amount of energy of these radiations per unit area. It depends upon the temperature upon which it is heated. Okay, so we have a black body, we heat it to a certain temperature. So here first temperature it is heated to 3500 Kelvin, 4000 Kelvin, 4500 Kelvin, 5000 and 5500 Kelvin. So you can see the energy density is changing with change in the temperature. So for each temperature you can easily see the energy density is increased. For example, this curve carries the energy density. So when it is heated at 3500 Kelvin, it has a low energy density as compared to when it is heated at the high temperature 4500 Kelvin. So you can easily see here it has a very high energy density. So the energy density or the energy of these black body radiations is increased with increasing in temperature. The another point you can easily see from this energy distribution diagram is that there is a wavelength. So there is a certain wavelength at which energy of these radiations is maximum, and this is true for each temperature. For example, when temperature is 3500 Kelvin, so there is a this wavelength which is around 800 nanometer at which energy density is maximum. But if you heat it at a very high temperature, you can see this wavelength shift towards the lower value. So at 5500 Kelvin, the energy density is maximum over a wavelength at around 600 nanometer. So the position of this maximum wavelength or the lambda max, you can say, shift towards the lower wavelength. So you can easily say shift towards the lower wavelength with increase in temperature. So it's also true, for example, when you heat this iron rod, as the temperature increased, it shifts towards the blue, now which is a shorter wavelength. So same is true here. This wavelength at which energy is maximum, so this is your lambda max, or the wavelength over which this energy is maximum, it shifts towards the shorter wavelength or the lower wavelength as temperature increases. So when the temperature increases, here this is a UV region, this will be a visible region, and this will be infrared region. So it shifts towards the UV region. The another feature of this energy distribution diagram is you can easily see is the curve. Now you can see this curve become more sharper. So here it is more flat curve at low temperature, but as the temperature increase, this curve become more and more sharper. So this curve become more and more sharper with increase in the temperature. Okay, so the energy distribution in this black body radiation as a function of temperature is given by certain laws, which were according to the classical theory. The very first law is the Stephen-Boltzmann law. So what the Stephen-Boltzmann law says that the energy of black body radiation is proportional to fourth power of absolute temperature. So this energy density, which is, as we already seen, it increases with increase in the temperature, but this law says This increase is directly proportional to the fourth power of absolute temperature over it is heating. So we can say energy is directly proportional. So we can say energy is directly proportional to the fourth power of temperature, and we can remove this sign of proportionality. So it can be write E is equals to A T the power 4, where A is a constant and it is called Stephen's constant. This A is called Stephen's constant. So it's a constant value. It has a constant value. It's called Stephen's constant. So this law is called Stephen-Boltzmann law. The second law is a Wien's displacement law, which deals with the wavelength distribution. And it says the wavelength, so we already know wavelength is decreasing with increased temperature. So wavelength of the spectral distribution is inversely proportional to temperature. So we can write the wavelength, or the lambda max, is inversely proportional to temperature. Or we can write multiply of this wavelength maximum with temperature is constant. So this sign of proportionality will remain as such, so it is a constant. So if we take as such, sign of proportionality is constant, so we have a constant here. So lambda max is equal to constant 1 upon t, or we can write by taking cross multiple, we can write lambda max into t is equals to constant. So this law is called Wien's displacement law. So these two important laws are given by for the black body radiations by classical theory. Okay, or these observations were given according to them. Now next is black body radiations and classical theory. Let us see how this classical theory fails to explain black body radiations. Now, as we already know, according to Maxwell's electromagnetic theory, the black body radiations are emitted by vibrating particles inside the body. So this Maxwell gives the electromagnetic theory for this black body radiations, or it is a classical theory. And what it says these black body radiations, they are emitted by vibrating particles, those particles which are vibrating inside the body of this black body. And these vibrating particles, they are called oscillators. And these oscillators emit energy in the form of electromagnetic radiations, and the frequency of these emitted radiations is equal to the frequency of oscillations of these oscillators. So what it means to say, according to this theory, it says the black body radiations are emitted by vibrating particles within the black body. These vibrating particles, they are called oscillator, and the amount of energy or the frequency of these emitted radiations is equal to the frequency of oscillator. More the frequency of these oscillator or the vibrating particles, more is the energy of emitted radiations. So according to this, it gives the two laws again. One is given by Wien's, it is called Wien's contribution. Now what Wien's consider, it says these oscillators or vibrating particles, they are of the molecular size, and based upon this assumption he derives the expression for the energy of these black body radiations. And the expression for the energy of black body radiation is given by, according to this Wien's, is E lambda is equals to 8 pi hc divided by lambda the power 5 exponent minus hc upon lambda k t. So this energy expression was derived by Wien's. We are not going to derive this expression, we will take it as such. But the drawback of this Wien's contribution is that it can explain the energy of these black body radiations at only low wavelength. It can explain the black body radiations at low wavelength, but it failed to explain the energy of black body radiations at high wavelength region. So the second law or the contribution was given by Rayleigh gene, and this Rayleigh gene says the black body composed of large number of oscillators, and it applies law of equipartition of energy among these oscillators. That means the energy is equally distributed among these large number of oscillators, and By using this, he derived expression for the energy of these black body radiations, which is given by E lambda is equals to 8 pi upon lambda to the power 4 k t, where k is a Boltzmann constant, t is a temperature, lambda is a wavelength. However, again, Rayleigh-Jean law explained blackbody radiations at high wavelength, but it failed to explain blackbody radiations at low wavelength. Now, because you can easily see energy is inversely proportional to the fourth power of this wavelength. So, as the wavelength will decrease, energy will also decrease without any limit. And this is also called ultraviolet catastrophe. Now, what's ultraviolet catastrophe? According to this Rayleigh-Jean's law, energy density is inversely proportional to the fourth power of wavelength. So, if we keep temperature constant, as the wavelength decreased, energy will also decrease. Energy will increase without any limit. So, this will be this is called ultraviolet catastrophe. Okay, so this was the this was all this was all about the black body radiations and classical theory. So here classical theory failed to explain this black body radiations at the low wavelength region and in high wavelength region. So this was the failure of classical theory. In next video lecture we will see how quantum theory can explain black body radiations. Thank you.